Hello, it's a new year for One Lone Coder, so let's have a nice simple video to get started. Let's procedurally generate the universe. Now, to those of you that frequent the Discord server, you will know that I'm a big fan of the Elite series of games, going way back to the early 80s, where the Elite games presented an entire universe on a very small machine, i.e. a machine with not very much memory. And over the Christmas period, I've been playing Elite Dangerous and loving every minute of it, and it has a vast universe. In fact, it has a universe so large it can't all possibly be stored on the computer. And so I've decided to create a small application here which tries to emulate that effect, and as you can see I'm panning around, well, a very simplistic looking universe of different star systems, so each of these circles represents a star. The first thing to note is that the universe is actually persistent, so if I scroll this way it will look the same as I scroll this way. Admittedly, it's easy to get lost in my universe because I've not put any coordinates on the screen. I shall add that to the to-do list. But please don't misunderstand, this universe is vast, it's huge. It will go on for billions and billions of stars, and they will all exist in exactly the same place. As I move the mouse cursor around, I can highlight specific stars. So let's click on this one. So we can click on this one and we see around the stars there's several planets, and the planets have several moons. Let's try a different one. Let's try a few. So some don't have any, but they all have something different, and again these are persistent, so I could go to one side of the universe and come back, these will still be here. We can test this. Let's try and find some features I can recognise. So here we've got a small cluster of planets. Let's pick that one in the middle, and I'm going to pan all the way this way for a few seconds, and then I'm going to pan all the way back and try and find that cluster. There it is. And click on the same one, we see we get the same results. And it doesn't matter how big this universe is, there's no search time required. It will always generate the same persistent star systems for a given star. The size of this universe is limited only by the precision of the integer types I'm using to store the position of the mouse coordinate. It is vast, and yet can be rendered and interacted with in no time at all. You can also see on the right hand side of the screen here that the universe consumes very little memory. As I'm moving around, we're not generating more and more planets and stars, so there's no more memory created. And nothing is cached out to disk, that would be far too slow. And you'll just have to take my word for it, but the size of the executable on disk is about 30 kilobytes. So how do we store an entire persistent universe and access it so quickly on my computer? Well, hopefully it's obvious that we can't store the entire universe on my computer. Instead, we're going to use an elaborate series of equations to generate the universe as we need it, and we'll use our mouse coordinates x and y as the input parameters to this equation. This technique is called procedural generation, and we see it quite a lot in games like Minecraft or roguelikes. Now, I'm going to take a little bit of an issue with that, and I'm expecting some debate in the comments about this. I think games like roguelikes, NetHacks and Minecraft and all of those games that generate random content, I don't necessarily consider those to be procedural generation. I think of that more as automated generation, because take Minecraft for example, it generates the world in these chunks. And once it's generated them, they need to be stored, they need to be fixed somewhere and recalled when they're required. In my mind, procedural generation is something a bit different. It is generating the resources that are required on the fly and consistently each time. I don't think either term is incorrect, but in my mind it makes sense to make a distinction between the two, that games that automatically generate resources and assets are not quite the same as games that procedurally generate resources and assets. At the heart of all procedurally generated applications lies randomness, or in the case of a computer, pseudo-randomness, because we can't realistically generate true random numbers. But randomness on its own is not enough to create compelling resources. We need to control that randomness in such a way that makes our application sensible. And in this video I hope to show just that. So let's get started. As usual, I'm going to start with a skeleton pixel game engine project. So it's got nothing in the onUserCreate and onUserUpdate functions, and I'm constructing the pixel game engine to be 512 by 480, and each game pixel is 2x2 screen pixels. Now I've also moved over to Visual Studio 2019 and I'm still learning what it's going to be doing with tooltips and things popping up all over the video, so I apologise if they get in the way. Fundamentally, procedural generation is about controlling randomness, and so I think it's worth spending a few minutes just exploring the available options of pseudo-random number generation that are available to us via the C++ language. And rather than just look at the statistics of the generated numbers, I'm going to visualize them instead. And I'm going to do that whenever the space key is pressed. If you've seen my videos before and we've looked at things like noisy images on the screen, it's always caused the YouTube algorithm to completely collapse when it's displaying the video. So by making it sensitive to the spacebar being released, I should hopefully be able to retain the integrity of the image, which is going to be necessary to understand whether a random number generator is good for us or not. There are two qualities of the random number generator I want to look at. The first is how good is the randomness, and the second is how fast can it generate the random number. So I'm putting in two little time points so I can measure the duration of the generation. And I'm going to draw that to the top left of the screen using the Pixel Game Engine's drawString function. My intention here is to go through every pixel on the screen. And for each pixel we're going to draw a random number, and depending upon the value of that random number I'm going to set a flag b is star to true or false. And I'll just simply for now use a single pixel as the star. It's either white or black. And the only reason I'm drawing the black stars, even though I've previously cleared the screen up here to all black, is to just make sure that the timing is consistent. For example, if the random number generator generated a few white stars, it's going to give the appearance that it's performing better. So I need to make sure that the drawing of the star is not factoring into the timing of the randomness functions. So let's start with the random function everybody knows, rand. And everybody also knows, or at least they've been told, that rand is not a very good random number generator. Well, let's take a look. So I'm going to draw a random number between 0 and 255 inclusive, and I'm going to check is that value less than 32. So in principle, we're looking at an eighth of the screen being stars, or white in this case. Let's run the application. Now to get any stars to appear I need to press the space bar, so there we go. And on average this told us to generate this field of stars took about 6 milliseconds, and the randomness doesn't look too bad. At first glance anyway. I keep pressing space, I can regenerate more and more stars. And the time to do so is, well, it's roughly always the same, a handful of milliseconds. The problem is, I want to control the randomness. It's no good to me to just have genuine randomness here. I need some way of shaping that randomness into a universe. If I always wanted to generate the same universe each time, I would need to seed the random number generator with some sort of key. I'm going to pick a value at random here, 1000. So now when I run the application, even though I'm pressing the spacebar and we can see it's generating it, the universe is the same each time. So knowing that we can set the seed of a pseudo-random number generator is going to be really important for maintaining persistence across the assets we're procedurally generating. But there's a problem here. In order to know whether a pixel is black or white, I need to have generated them in this specific sequence from the top left all the way to wherever my cursor is. So yes, I can always check what colour the pixel is under the cursor, but if I wanted to derive that based on our randomness equations, how do I do it? Right now I have to start at the top left and generate the sequence precisely because of the set seed, all the way until the point that I need it. This could be very slow, particularly if I've got an entire universe to procedurally generate. I would have to generate the universe up until the point that it is under my mouse cursor. And this is exactly what I'm not trying to do. I don't want to have to generate the universe in advance and store it somewhere in order to interrogate it or assess various components of it. What if instead we used a seed that was based on the spatial location within the universe? So instead of setting the seed once at the start, I'm going to set it for every single star that we generate. But there's no point in me using a fixed number all the time because then the entire universe would be the same. Instead, I'm going to take the X and Y position of the screen and sort of squash that together into a seed value and use that as my seed. This approach guarantees that the seed is different for every pixel on the screen. Yet regardless of the location, it should consistently generate the same sequence of random numbers for that location. Let's take a look. Just press the spacebar. Well, it's certainly generating numbers and it's plotting stars and it's taking a little bit more time now that we're setting the seed. But something tells me that's not quite random. Perhaps I'm just getting very, very unlucky with the distribution, so let's change that to a 50-50 distribution. Well, that's not changed very much, and in fact this highlights the limitations of using rand. Given that we're choosing to plot a pixel as white or black based on the first random number generated after setting a seed, these patterns suggest that the random number is highly correlated to the seed. Therefore, it's barely random at all. In fact, it's utterly predictable in this instance. So rand is rubbish. We're going to need something better than rand. Modern C++ actually provides a good random library as part of its standard library. Generating high quality and robust random numbers is well beyond the scope of this video. And it's a complete computer science and mathematics field in its own right. There's a lot of research and dedicated effort going into generating high quality random numbers, simply because they underpin all of our digital communications and cryptography services. And as I've just demonstrated, even though we've used rand plenty of times in previous videos, it's great for little bits of randomness in games. If you are really relying on its integrity to generate random numbers, it could probably very easily be hacked. I think generating random numbers on computers is a fascinating topic. I don't know if it will ever be solved until we get dedicated hardware which can somehow exploit the environment in order to generate some random numbers. But until then, we've got what we've got. In good old modern C++ fashion, using the random library is a little bit wordy. First, we have to choose some sort of random device. This is meant to be the seed that will be generated randomly from my machine. Then we need to choose what kind of random number generation engine do we want to use. And in this case, I'm going for the Mersenne twister. It's reasonably accepted as being one of the most robust random number generators out there. At least a lot of research has gone into it. I can't just draw a random number like before, I need to specify a distribution. And in this case I'm specifying a uniform distribution, so all numbers should have an even probability of being drawn. So this time let's include the standard random part. And just as we did before, we'll do the same test. I'm going to draw a random number between 0 and 255 inclusive and plot the pixel. You'll note that I've not included this setup within my time period. Ideally you'd only need to do this once. One final thing, just because I forgot, we need some parentheses after the RD in the construction of the Mersenne twister object. So let's take a look. So as before, I'm going to press the spacebar, and well, it looks pretty much the same. If anything, I would say it's a little more evenly distributed than it was using rand. Not seeing quite as many clusters or line artifacts. It might just be my eyes playing tricks on me, but it does seem to look better. And it's taking approximately the same time, about 3.8 milliseconds, 4 milliseconds there, generate a few more. So that's fine. But again, we've got this problem of we've just set the seed once for the entire universe. Now we need to set it per star. Well, using the same seed generator as before, I'm just going to seed the Mersenne twister. And let's try that. Press space. And wow, oh dear, I mean, it looks great, it's perfect for what we want, but it's taking about 400 milliseconds, 395, 400 milliseconds to generate the screen. It looks like seeding the Mersenne twister algorithm is quite slow, and probably far too slow for our needs. However, it has generated a very nice random universe. So I could place my mouse cursor anywhere in this scene, and converting its coordinates to use as a seed for the random number generator will tell me whether the star exists or not. Is the pixel white or black? And so the quality of the random number is brilliant here in this case, but the performance of it sucks. We need something that's a good in-between. So C++ random library Mersenne Twister, you're out. It takes far smarter people and more dedicated people than me to generate a high quality random number generator. So I would suggest go and finding one, and one that's been around for quite some time is the Lemma or Lemma random number generator. I was using this back in the early 2000s as part of a research project I was doing for the university. This was before the introduction of the random library, where you had easy access to algorithms such as Mersenne Twister. This algorithm is known as being reasonably robust, but the beauty of it, and what's going to appeal to us, is that it's actually very, very quick. We're going to need to create a little utility function to generate these Lemma random numbers. Now, if it's not pronounced Lemma, then I apologise to Dr. Lemma. So I'm going to create a small function called Lemma32, because it's going to generate 32-bit numbers. Most of the algorithms shown for this generate 64-bit numbers, and by converting it to 32-bit, I've probably completely compromised its integrity as a robust random number generator. I'm aware of that. It works by maintaining a state variable. And each time we draw a random number, we're going to change that state. In fact, that state is the random number. And even though this will look like gobbledygook, that's all there is to it. And we can see computationally there's not a great deal going on here. We've got some additions, we've got an integer multiplication, but then all we've got are shifts and XORs. These are all very cheap computational instructions to use. And the maths behind this is mostly beyond me, but I'm on the understanding that these are some type of specialist prime number, and by XORing with these prime numbers and shifting the register, we can change the state of our Lemma variable. In many ways, this is very similar to a linear feedback shift register. So let's just get stuck in and use it straight away. Instead of looking at the whole screen this time, we're going to look at just setting the seed value directly to be the Lemma state, so that's sort of priming the shift register. And as we have done exactly before, I'm going to draw a random number between 0 and 255 inclusive. So let's take a look. Press space, and what we see now is a persistent universe being generated per pixel on the screen with the same performance as rand. And so this is perfect for what we need. Procedural generation is fundamentally harnessing the properties of probability to generate interesting things. So let's just take a very simple one-dimensional example. Let's assume I've got a plane of land, and I wanted to populate this land with trees. In the universe example, we're using the location in space as the seed for a random number generator, so I'm going to do the same sort of thing here. And I'm breaking space up into discrete zones. For each zone, I'm effectively rolling a die and making a decision based on the output. So I can assume, with my die example, that a tree exists if my random number is less than 2. In this case, there's a 33% chance of a tree existing. So we might see one here, and one here, and one here, etc, etc. If I made this threshold larger, let's say if it's less than or equal to 5, so there's only a 1 in 6 chance of it not being a tree, we would certainly expect to see a lot more trees in each section, to the point where they're all uniformly distributed across the land. In order to bias procedural generation to give us plausible results, we can't just rely on the probability and harsh thresholds alone. In this tree example, we may see that if we did have the probability of it being a tree set too high, all of our trees would be uniformly spaced. It wouldn't look particularly realistic. Perhaps we want clumps of trees to exist instead. Well, this is just a case of biasing our threshold values on some other parameters. Perhaps the threshold value could be based on location. So as the location number increases as it's going across the screen, the probability of it being a tree also increases, at which point it's unlikely we'd see a tree here at the start, but as we're moving along the screen we may start to see them, and we'll start to see them with more frequency. So you could use this approach to have sort of a boundary going into a forest, for example. We can also use lots of other interesting functions to act as this threshold. Perhaps we wanted a clump of trees to appear somewhere in the middle of this land. Well, if we used a threshold value that was biased by some other function, for example, a Gaussian curve, then in this region it's far more likely we'll see trees than in these extreme regions. The beauty of this approach is that our random number has never changed, but our understanding of how we want to construct the world has forced us to think about how to manipulate the results of that drawn random number. And this is really down to us as engineers to devise an appropriate solution set of rules to construct compelling worlds. And I'm not arguing that that in itself is easy, it's far from it depending on the level of detail you want to go to. But fundamentally, the random component is at least guaranteed to be consistent. And so, irrespective of how complicated your generation routine is, it will always be the same each time. So, given that we know we're going to get the exact same sequence for a given seed, and that sequence is going to be random, I'm going to construct my universe by first checking for that location, does a star exist? And so that becomes my first random number draw. I'm going to draw a maximum up to 20 and I'm going to test, is that equal to 1? That will tell me, does a star exist? So 1 in every 20 locations will contain a star. Now it's important I don't reset the seed because I want the sequence of random numbers that are generated to be the same every single time. So the seed has been set once and we've generated, does a star exist? If it does, then I'm going to determine the size of the star. And again, that's going to be some random number generated, in this case, between 10 and 40. These units are meaningless, and they will need to be chosen to suit the application that you're trying to procedurally generate. Then I'm going to draw another random number for the colour of the star. And I've got 8 possible colours to choose from. And then I want to generate how many planets surround the star. And then for each planet in order, I want to determine some properties of the planet. What is its size? What is its temperature? What is its makeup? i.e., what percentage is perhaps covered in foliage? What percentage is covered in water? How much of it is minerals? You can make up all sorts of different parameters. What is its population? Each time we start to create a statistic, we always draw some random number from our pseudo-random number sequence. The sequence is always going to be the same each time. That's the real take-home message. And what the interesting thing is, we can start to not only just use the sequence, but we can use the values of parameters we've already chosen. So let's say we were also maintaining the distance away from the star. Well, we could use that distance function as part of the temperature calculations. We can use the temperature calculations to tell us, is it likely there's going to be water on the surface? And if there's no water on the surface, what's the probability of there being foliage? So this is really up to the designer now to start thinking, how are all of these things connected? But the beauty of this is it's generated when it's needed each time. Because even though randomness is involved in the definition of the planets and the stars and the systems, the randomness is under our control and it's guaranteed to be consistent. But the key principle here is we have to generate these random numbers in the same order each time. Now we've explored the randomness, I'm going to remove this code from the application. And I'm going to add to the application a new class which represents a star system. And the constructor of this class is going to be the thing that does all of the work. So I'll add a constructor which takes in an x and y coordinate, which is the location of this star system in the universe. I'm going to take our little random number generator from before and move that over to the class. We'll keep those private. The first thing this star system needs to do is generate its seed based on its location, which, as we've just seen before, is merging together the x and y coordinates. Now, I'm using a 32-bit system here, but I'm only looking at the least significant 16 bits of the x and y coordinate. That will, of course, put some boundaries on the universe. They will only have 16-bit coordinate resolution in each axis. So it's not going on forever, and hopefully when it does get to one end of the universe, it should just wrap round to the other quite nicely. Of course, if we needed larger universes, we would use more bits. as we start to procedurally generate the star system, we're going to need to store some of its states. So here I've added a boolean for whether it exists, something that represents the size of the star and the star's colour. And I'll draw the star's colour from an array of colours which I've defined as a const expression at the start of the program. So these are alpha, blue, green, red in hex. I don't always want to draw random numbers of the type unsigned integer 32. Instead, I'd rather work with doubles and regular ints. That's a bit more convenient. And also I want to work with numbers that are within boundaries that are sensible for the things I'm trying to define. So I want to create some utility functions where I supply a minimum and a maximum each time. So this one will generate a random integer between this minimum and that maximum. And this function will return a random double with the same constraints. Note that they both call the Lemma 32 function. So going back to our constructor, we can start to generate this system. Firstly, does it exist? And that's quite important and quite an odd concept, because you might think, well, of course the system must exist, we're constructing a class that represents that system. Well, that's not quite true. We're actually creating a definition of what exists at that location within the universe. So our boolean star exists will be set to true 1 in 20 times on average. If the star doesn't exist, I'm just going to abort the construction. There's literally no point in doing anything else. So very cheaply, we have set the seed, determined whether the star exists or not, and if it does, then we go on to create more interesting features. If it doesn't, then who cares? Assuming the star does exist, then I'm going to generate something that represents its diameter and choose its colour from the array above. Instead of working with the screen in a per pixel basis, I'm going to break the screen into sectors, which is easily done by taking any location on the screen and integer dividing it by the dimensions of our sector, which I'm going to set to 16 by 16 pixels. This allows me to then take the size of the star that we've just generated, and in some cases we'll have small stars, and in some cases we'll have big stars, and then we'll have some medium stars, but it gives me space to plot them. In this little simple demonstration, I'm just going to draw a circle of the appropriate colour, but you could of course procedurally generate images, you could create animated graphics. The possibilities are literally limitless. It just depends how much effort you are prepared to put into generating the detail required for your application. In the onUserUpdate function, I'm going to start drawing our world. So now we will clear the screen to black. And I'll create two variables, nsectors x and nsectors y, which tells us how many sectors we've got across and down the screen, because you might choose a different resolution and sector size. This year I'm going to get into the habit of using the built-in vector types in the Pixel game engine. So here I'm creating a two-dimensional integer vector called screen sector, which is going to hold the coordinate of a particular sector on the screen. I want to iterate through all of the sectors that are visible on the screen. So I have two nested for loops that are just scanning through all of the x and y coordinates, and because our sectors are quite large, there aren't that many sectors to process. For a given sector location, we need to determine what is the star system in that sector. So I'll construct a star system object, but I'll need to pass in the location. Which will be used to seed the Lemma generator later on. At this point, I'm only interested if the star actually exists. Now that will have been set by the procedural generation routine in the constructor of C star system. And as you'll see with the rest of this video, I'm really just going to hack in the graphics appropriately. So here I'm going to draw a circle in the middle of our sector, and I've got some hard-coded numbers in here. I know I shouldn't. But the point of this video is not about the visualization, it's about the generation. So this will just draw a filled circle based upon the size of the star, which already we now know because we have a star system object, and the colour. So let's just take a quick look. That's very nice. We can see we've got a variety of different size stars. Not every single sector is populated with a star, and the stars are different colours. But right now our universe is very, very small because we can't move around in it. If we want to move around the universe, we need to know where we are within the universe. So I'm going to create a 2D vector called galaxy offset. This effectively represents the camera location inside our universe. And in onUserUpdate, before we draw anything, we're going to handle some user input. I'm going to be sensitive to the W, S, A and D keys being pressed to change the value of our galaxy offset vector by a fixed constant speed. Don't forget, in the Pixel game engine, if we want movement, we need to modulate by f elapsed time to make the movement smooth, because the frame rate will vary depending on the load of your computer, but you want it to move at a consistent visible rate. We've done that many times before. This galaxy offset vector effectively represents the top left of the screen, and our nested for loops going through all of the visible sectors on the screen should be added to that offset to give us the real location in space. So to our screen sector variables, I'm going to add in our galaxy offset. There's X and Y. Now we should be able to move around the universe smoothly. So if I move this way, and we can see the stars are consistent going back. It's a bit of a bold statement for me to say we can see the stars are consistent, because none of us have memories that are that good. But let's just test the theory. So here I've got a big cluster of planets. Hopefully that should be recognizable in the future. Let's mentally clock that one in. And I'm going to scroll down for quite a while. There we go. And I'm going to scroll back up. And hopefully we should find that cluster of planets again. Maybe that will demonstrate that it's consistent. There it is. Now we've not stored that anywhere, we've generated that cluster dynamically on demand when we need it. But because we've got complete control of our sequence of random numbers, it is the same as having generated it previously and stored it. Because we don't actually care about the numeric value of our seeds, the fact that our galaxy offset vector is going negative and positive depending on where we are in the universe doesn't matter. It will always generate the same sequence of random numbers. Now that we've got this vast universe, it would be useful to be able to interact with it sensibly. We've got billions of planets. We don't want to have to search through all of the planets to find which one have we selected, what's its location. And of course now we don't need to. We know where our mouse cursor is going to be within the universe's space, so we can just interrogate that sector location and get all of the information procedurally generated immediately for us to use as we see fit. So I'm going to add in some mouse user input too. I'm going to get the screen space mouse coordinate and divide it by our number of sectors. So again, now we know which sector across the screen our mouse is in. But because we can offset the galaxy, we also need to now offset our galactic mouse cursor. So this vector represents the mouse on the screen, but this vector represents our mouse within the universe. As we're drawing the stars out on the screen, we can highlight which star might be underneath our mouse cursor. Of course, it can only be underneath the mouse cursor if it exists. So all I'm going to do is check whether the screen's mouse sector coordinate is the same as the sector coordinate we're currently drawing to. And if it is, I'm going to draw a circle around that sector. Let's take a look. And there we can see a nice yellow circle around stars, and it only appears where they exist. So I've not had to do any searching in this instance, and as I pan the screen across, we can see occasionally we get a little circle popping up as I accidentally put the cursor over a star system. But it doesn't matter where we are in our universe, it can immediately determine whether a star exists there. Universes with just stars in are all well and good, but not very realistic. Star systems need to contain other bodies. So I'm going to create a structure called S-Planet, and this is going to contain all sorts of different information about the planet, and I'm not interested, and I'm not even going to implement most of it. I'm just leaving it here as an example that actually you can create this as detailed as you like. You've just got to follow this process of always generating your random numbers in the same order. And each planet, not only is it going to have a bunch of material properties, it may have a ring, and it's going to have a selection of moons. In our star system constructor, there is no need to keep generating things if we know that we don't need them. For example, when we determined that a star didn't exist, we immediately aborted the construction. This means we could easily put gates within our system that will generate only up to the level of detail that we require. So I'm going to add a boolean as a simple example up here of generate full system. When we're in the galaxy map view, which we've just been scrolling around, I don't care whether the stars have planets or not. All I care about is whether the star exists. It's only when I select one of the stars do I then need to go and generate a star with all of the planets. And so if I don't care about generating the full system, I'm just going to return immediately. All I cared about was generating what does the star look like. But now I do care what the planets look like. And we'll get through this pretty quickly because I think we're getting to the point where I'm just repeating the same point over and over. But to generate a planet, I'm going to choose a random distance from the star because they don't all exist at uniform distances from stars. And I'm going to generate how many planets there might be. I'll create a for loop to then go through all of these planets one by one. And for each planet I'll create my planet structure and I'll start to populate it with some of the information. So each time I'm drawing more and more randomness from our sequence of pseudo-random numbers. None of these numbers really are going to make any difference to this demonstration. Although it did occur to me that if you wanted to describe the makeup of a planet like this as percentages, then you can't go over 100%, so you probably want to normalize those numbers. All of this is utterly irrelevant to procedural generation, but I wanted to sort of demonstrate that once you start generating these very random bases, you can manipulate this randomness as you see fit, based on real-world equations, based on previously drawn random numbers. You could even go as far as to generate modifications to these random numbers based on the neighboring stars in the system, if they exist or not. You can also do interesting things with the probability distribution. So here I've chosen a population value and it's choosing a random integer between, oddly, -5 million and 20 million. Now you can't have a negative population, but by using the max function in conjunction with this, some planets just will have no population. So it's sort of doing a 2-in-1 calculation with the probability here. If we wanted to look at percentages like we did with these, whether the star system exists or not, does this planet have a ring? Well, we'll draw a random integer and see if the value is equal to 1. So there's a 10% chance in this case of the planet having a ring. Perhaps the planet has moons. Well, in the same way as we've done the population, by taking the maximum of a range which can go negative and making sure that that maximum is always greater than 0, we can generate a proportion of planets that have moons and a proportion that don't. So in this case it's approximately 50-50 whether the planet will have at least one moon. And therefore if it does have moons, we'll create a loop that goes through all of the moons. And all I'm interested in is the size of the moons. Nothing stopping you then going creating more and more planet bodies. Do the moons have their own unique mineral systems and properties that you want to try and generate? Once we've fully populated a planet, I'll add it to the star system's vector of planets, which we'll need to add as one of its variables. Back in the onUserUpdate function, let's display the star system for a selected star. To handle mouse clicking, I'm going to be sensitive to the left mouse button being clicked. If it is, I'm going to generate the star system object based at the location of the mouse coordinate in the galaxy. And if it exists, I'm going to record the fact that it has existed by setting a flag to true. I also want to cache that particular location. At the moment, I don't care about the planets and the moons, so I've not instructed the star to be constructed with all of its planetary detail. If the star at that location didn't exist, I'll set my selected flag to false. I'll just add these variables into the class. There's my star selected and my star selected vector. Now that we know we've got a system selected and we know its coordinates, we can go about drawing it on the screen. And I'll quickly go through this because I'm not interested in demonstrating the actual drawing routines. I want to display on the screen the entire system now. And we know that we only need to do that if our star selected value is true. But now I am interested in generating the full system. You'll see a lot of magic numbers creep in now. These are just to position things on the screen nicely. They're actually unimportant to any of this algorithm. But firstly, I'll want to draw a window. The blue window that's going to hold the information for our star. And I also want to draw the star on the left-hand side of the window. So all of these coordinates and scaling factors are just to make it appear on the screen in a pleasing way. We'll just take a quick look to see if things are working so far. So I can select a star, and then we've got our blue window, and we see the star is the same colour as the star chosen in the universe. And if we choose a bigger star, it's a bigger rendered star in our blue window. Let's choose this little tiny star over here, and as before, we can move to anywhere in the universe and continue doing the same thing. If we select somewhere where a star doesn't exist, the window disappears. Once we've drawn the star, we want to draw the planets that orbit the star. And so here I've got a little auto for loop that's going through the vector of planets associated with the star system. And again, things are scaled and positioned accordingly. The planet may have some moons, in which case we need to then have another for loop that goes through the vector of moons for that particular planet. All of my planets are just drawn as filled circles. And so let's take one final look. There's our universe. Let's choose a system. We can see the planets with associated moons of different sizes around those planets. There's all sorts of variety, and we know, even though I've not visualized them, that these planets have different properties too about their composition and makeup. And because we've used procedural generation with a high quality random number generator that's very fast, we're guaranteed that we can always come back to a known position in the universe and it will be generated exactly the same way. And so there we have it, a persistent and procedurally generated universe, all stored within about 200 lines of code and some fancy random number generation. This has been a very simple demonstration of this concept, but I'd like to go back to a point I made at the start, that it's not necessarily the same as, for example, the Minecraft procedural generation routines. Nothing here is persistently stored, it's always generated as and when it's needed. And this does cause some problems of its own. How do we change the state of this universe? In Minecraft, for example, the player will go and change the state of the blocks that are created. That's quite tricky here, and I think that's definitely going to be the topic for a future video. As always, the source code for this video is available on the GitHub from the link in the description below. It's got a few more comments and a bit more material inside it. If you've enjoyed this video, please give me a big thumbs up, have a think about subscribing, perhaps come and have a chat with me and many others on the Discord server. A big thank you to all of my patrons or Patreons depending on where you're from, and I'll see you next time. Take care.